Right now, tonight, somewhere past the orbit of Jupiter, an ancient visitor from another star system is quietly leaving our solar system for good, and it will never come back. But that's not actually the part of this story that should keep you up at night. The part that should is this. Astronomers are now almost certain that a fourth one is already on its way in. And this time, humanity might actually have enough warning to do something about it. This is the story of what comes after 3-Eye Atlas, why a brand new telescope in Chile is about to change how often we spot these things completely, and why the next few years could determine whether we ever get a real close. Look at a piece of another star system or simply watch another one vanish the way the first three did. Before we get into it, if you're new here, this channel covers space and astronomy stories the way working scientists actually talk about them without the exaggeration. If that sounds like your kind of channel, the subscribe button is right there, and it genuinely helps this content reach more people who care about getting the science right. To understand why the next few years matter so much, it helps to understand exactly how badly we've been caught off guard every single time so far. The first confirmed interstellar object, Oumuamua, was spotted in October 2017, and by the time astronomers realized what they were looking at, it was already on its way out, receding fast, tumbling end over end, in a way that suggested an unusually elongated shape. Telescopes around the world scrambled to point at it in the handful of weeks they had left, and then it was gone, too faint and too far to study in any real detail ever again. The second, Borisov, discovered in 2019, gave researchers a little more lead time and behaved much more like an ordinary comet, but the same basic problem applied. By the time anyone knew it was interstellar, the observing window was already closing, and the third 3-Eye Atlas, found in July 2025, turned out to be the most scientifically productive of the three by far. Studied by the James Webb Space Telescope, Hubble, the Very Large Telescope, and even NASA's Perseverance rover during a close pass by Mars. But even that mission was fundamentally reactive. Every single observation of 3-Eye Atlas happened after the fact, astronomers racing to squeeze out as much data as possible before it faded. From view for good, rather than planning years in advance for a target they already knew was coming. That pattern, discover it late, study it fast, watch it disappear, has defined every interstellar encounter humanity has ever had. And it's exactly the pattern astronomers are now trying to break. The reason they think they finally can comes down to one facility, the Vera C. Rubin Observatory, perched at Cerro Pachon in Chile. It houses the largest digital camera Eve small car, attached to a telescope, specifically designed to photograph enormous swaths of the sky, over and over again every single clear night for the next 10 years, as part of a project called the Legacy Survey of Space and Time. Rubin isn't hunting for interstellar objects exclusively. Its job is to catalog, essentially everything that moves or changes in the observable sky, asteroids, supernova, distant galaxies, all of it. But that relentless, repeated coverage happens to be exactly the kind of survey strategy that gives an interstellar object its best possible chance of being caught early, while there's still real time to react. Here's why that distinction matters so much. Atlas, the survey that found 3-Eye Atlas, was built primarily to hunt for asteroids that might threaten Earth, and it only stumbled onto an interstellar object as a byproduct of that broader search. Rubin's entire survey strategy, by contrast, is built around scanning the same patches of sky again and again, comparing each new image against the last one to flag anything that has moved. For something arriving from outside the solar system, that kind of comparison is exactly what's needed, because these objects tend to be faint right up until they get relatively close. And the only way to catch one early is to already be looking at the right patch of sky when it crosses into view. Astronomers involved with the project have said plainly that they expect Rubin to find many more interstellar objects in the years ahead, possibly dozens over the coming decade. A dramatic jump from the 3 confirmed sightings humanity has managed across the previous 8 years combined. Some researchers have already started informally referring to whichever one turns up next as 4-Eye, regardless of when or where it's actually found. It's a small, almost offhand detail, but it tells you something important about where the field's confidence currently sits. Nobody serious in this area of astronomy is asking whether there's a next one anymore. The consensus has shifted entirely to when, and increasingly to how much warning we'll actually get this time. It's worth being honest about why that shift in thinking happened so quickly, because it isn't just optimism about a new telescope. Researchers studying the population of interstellar objects have increasingly come to believe that these things have been drifting past the sun since the earliest days of the solar system, essentially constantly, and that we simply lacked the technology to notice them until the last decade. If that's true, the 3 we found so far, Oumuamua, Borisov, and 3-Eye Atlas, aren't rare anomalies at all. They're just the first 3 we happen to be capable of seeing, out of what could be an enormous continuous population passing through on a regular basis. Some estimates, based on the frequency of these first 3 discoveries, suggest interstellar objects may pass through the inner solar system far more often than anyone assumed before 2017, most of them simply too faint or too distant for older survey telescopes to ever catch. So what would actually change if Rubin catches the next one early? This is where the story stops being about mere cataloging and starts becoming genuinely exciting from a mission planning perspective. With enough advance warning, weeks or ideally months rather than days, mission planners could potentially redirect existing spacecraft that are already out in the solar system toward a flyby, the same way that European Space Agency's JUICE spacecraft, already en route to Jupiter's icy moons, managed to attempt its own observations of 3I Atlas as it happened to pass nearby. That was opportunistic and limited. A properly planned intercept with enough lead time could be something else entirely. In fact, that exact idea already has a name and a growing body of serious engineering work behind it. Mission concepts, sometimes referred to as rapid response. Interstellar object missions have been studied by research teams and space agencies. Specifically for this scenario, a small, relatively low-cost spacecraft kept ready or launched quickly, specifically to intercept the next confirmed interstellar visitor while it's still close enough to reach. The basic challenge is brutal physics. These objects move so fast, tens of kilometers per second relative to the sun, that there's a genuinely narrow window between when an object is discovered and confirmed as interstellar and when it becomes too far away and moving too quickly for any realistic spacecraft to catch up to. Earlier detection directly translates into a wider launch window and a gentler, more achievable trajectory. That's the entire reason Rubin's early warning capability matters as much as it does. It isn't just about getting a better photograph sooner, it's about buying enough time to actually reach one of these things with real instruments, rather than just watching it through a telescope from 90 million miles away. It's worth pausing here to be clear-eyed about how difficult that would still be, even with more warning. A dedicated flyby mission would need to be built, tested, and ready to launch on short notice, essentially sitting on a shelf for years, possibly decades, waiting for a target that might not show up on a convenient trajectory for a very long time. Space agencies have to weigh that kind of standing readiness against dozens of other missions competing for the same limited funding. And even with Rubin's improved detection capability, there's no guarantee the next interstellar object found will be on a trajectory that's actually reachable. Some paths through the solar system are simply too fast, too distant, or too poorly timed relative to where Earth happens to be for any spacecraft to realistically catch up. Rubin dramatically improves the odds of early detection. It doesn't guarantee a catchable target will show up on the first try, or the second, or possibly for years afterward. Still, the scientific case for trying is difficult to overstate, and this is really the heart of why any of this should matter to you. Every comet and asteroid in our own solar system formed from the same disk of material that built the planets, which means studying them mostly teaches us about our own local chemistry, conditions specific to our own corner of the galaxy. An interstellar object is something else entirely, a physical sample of material that condensed around a completely different star, under different temperatures, at a different point in the galaxy's history, drifting here across potentially billions of years, without ever being disturbed until it finally crossed paths with our sun. 3I Atlas already demonstrated exactly how valuable that kind of sample can be, giving researchers a direct chemical comparison point that helped test whether the process of building icy bodies works the same way throughout the galaxy, or very significantly depending on where and when a star system happens to form. A dedicated flyby, with real instruments flown directly through an object's coma rather than observed from a distance through a telescope, would take that kind of comparison to an entirely different level of detail. The difference between studying a planet through binoculars and actually landing a rover on it. There's also a planetary defense angle worth mentioning, honestly, even though every interstellar object found so far has posed zero risk to Earth. NASA and the European Space Agency were both explicit and consistent that 3I Atlas never came remotely close enough to be a realistic concern at any point in its journey. But interstellar objects move on trajectories and at speeds unlike anything native to our solar system, and improving our ability to detect them early, track them precisely, and understand their composition quickly is exactly the kind of capability that matters regardless of whether any specific object ever poses a genuine threat. Rubin's survey strategy, built primarily to catalog potentially hazardous asteroids in the first place, happens to serve both purposes at once. So, where do things actually stand right now? Rubin's 10-year survey is underway, systematically imaging the sky in a way no previous telescope ever has, generating hundreds of thousands of alerts on a single active night. each one representing something that moved or changed since the last time that patch of sky was photographed. Researchers involved in interstellar objects, studies have said openly that they consider it a matter of time, not a matter of if, before the next one turns up in that data, and that whenever it does, the amount of advance warning astronomers get could be dramatically longer than anything available for Oumuamua, Borisov, or even 3I Atlas. Whether that translates into an actual spacecraft reaching one of these things depends on a combination of factors nobody can fully control: funding decisions, launch readiness, and above all, the simple luck of whether the next object happens to arrive on a trajectory anything could realistically catch. If you've stuck around this long, you already know this isn't the kind of story with a tidy ending, because it doesn't have one yet. What's actually coming next is more watching, more waiting, and a genuine, non-hypothetical chance that within the next few years, telescopes will catch something moving through our solar system on a hyperbolic path, early enough that humanity gets to make a real choice about what to do next, rather than simply racing to observe whatever's left of the window before it disappears again. Somewhere out there. Tonight, that object may already be inbound. Nobody on Earth knows it yet. But for the first time since we started finding these things at all, we might actually be ready when we do. If this kind of deep dive into real, sourced space science is what you come here for, subscribing helps a lot. Let me know in the comments whether you think humanity will actually manage to launch a spacecraft toward the next interstellar object in time. It genuinely shapes what we cover next. And sharing this with someone who'd get a kick out of it is the easiest way to support the channel.